So in this video, we'll be working these problems. This is a sheet that I gave you with more Hardy Weinberg practice on it. And so thought it would be good for us to go over it together in class or in this video. Some pretty strange problems here. I think one year I was helping with homecoming decorations, and I just was walking through the hall and saw some strange things, and I just decided to write some problems about them. So that's where we get this crazy stuff. So let's look at the first prompt. Upon entering the freshman hall, an unnamed biology teacher at Murray High School made an astonishing discovery. There was a tiny population of paper dolls living on the wall. One observation he noticed is that there was an unusually high percentage of albinism in the population. Albinism is a recessive trait which is found in 1 in 17,000 humans. So everything I've read up to this point is just filler garbage. The population on the wall showed a staggering 47 in 135 paper dolls have albinism. With that information, answer the following questions. Now, I said it was all garbage. That's not 100% true. We did learn that albinism is a recessive trait, and so if albinism is a recessive trait, that means that it only shows up when both alleles are recessive. And we also know that 47 in 135 have that trait. And so if you remember in the last video and all along what I have been telling you, what is the key to success in solving these problems? Once you find Q squared, which Q squared again is the percentage of homozygous recessive individuals in a population. And so once you find the Q squared and solve for Q, then you get P, and then you've unlocked the entire problem. And so in this problem, we are given the percentage of individuals with albinism, not the percentage, we're just given those numbers, but we know it's 47 out of 135. And so if it's 47 out of 135, pull up my trusty calculator here, and we see that that is approximately 35%. We're going to round it up. So 35% is equal to Q squared. And so what does Q equal then? I learned how to do square root, I think. I did. So 0.59 is going to be our Q, which means that P is 0.41. And you may be wondering, I did all of this without even reading what the problems were, because again, now that I know this information, I'm able to solve every bit of this. Whatever problems it might throw at me, I'm going to be able to solve them. And so let's look at number one. How many recessive alleles are there in the population? All right, so it's asking me not for a percentage, but it's asking me for an actual number of alleles. I know that there are 135 individuals in the population, so there are 270 alleles because every individual has 2 alleles for this gene. And I also know that the percentage of recessive alleles in the population, which is equal to Q, is 59%. And so I'm going to take my 270 and I'm going to multiply that times this 57%. And I'm going to get 159.3. Now, when we're talking about alleles, obviously we can't have 0.3 alleles. And so you can just round to the nearest whole number in this regard. So we'll say 159. How many dominant alleles are there in the population? Well, we know that there are 270 total alleles, 159 of which are recessive. And so whatever is left is going to be the dominant alleles. And so that would be 270 minus 159. And so that is 111. If you'd like, we can check our math. And we can make sure that that's the case. We can take that 270 and multiply it times 0.41. And there you go. How many heterozygous carriers, or how many are heterozygous? are carriers for the albino condition. Again, it's not asking us for a percentage, so we have to be careful here. There are 135 individuals in this population, and I need to know how many of those are heterozygous. And so how do I do that? Well, I know the percentage of heterozygous is equal to 2PQ. And so I'm going to multiply 2 times 0.59 times 0.41, and that is my percentage of heterozygous individuals. And so then I'm going to multiply that times the total number of individuals to get 65.3 individuals. Since we don't want a 0.3 of individuals, we're going to say 65 of them are heterozygous. And then what is the percentage of the population that is homozygous dominant? If you remember, the percentage of homozygous dominant individuals in a population is equal to p squared. And so I'm just going to take 0.41 and square that, and I'm going to get, rounded up, 0.17. Pretty straightforward. Let's go on to the next problem. As he, I guess talking about the previous biology teacher, turned down the junior hall, the teacher noticed that there was yet another population of wall-bound creatures. This time the creatures were only heads, with no arms and no legs. They liked to swim, and their name was Bob. Up to this point, we've been given no useful information. Of the 335 Bobs on the wall, 14 had the unfortunate distinction of having a football-shaped mouth, which is a trait that is retained from a larval stage. This is a recessive condition. With that information, answer the following questions. And so 14 out of 335 have the recessive condition. So again, just by way of review, the percentage of those individuals with a recessive condition is Q squared. And this is what we're trying to solve for, because that is the key to unlocking the magic of Hardy-Weinberg. And so 14 out of 335 represents that Q squared. And so let's do that math. 14 divided by 335 gives us 0.04. And if you go ahead and take the square root of that, because 0.04 equals Q squared, right? Let me write that down. So this is 0.04, and this is also equal to Q squared. And so Q is going to equal 0.2. Nice, easy number for us. So if Q equals 0.2, then we know that P equals 0.8. And so now that we have that info, let's reproduce it up here so that we can deal with this problem. Let's answer these questions. What is the percentage of recessive alleles in the population? We did this already because Q is equal to the percentage of recessive alleles. And so this is 20%. What is the number of dominant alleles in the population? So we're asking for a number here. We know the percentage of dominant alleles is 80% or 0.8. We know that there are 335 individuals. So if there are 335 individuals, there are 670 alleles. Where did I get that? 335 times 2. Every individual has 2 alleles. And so in order to figure out the number of dominant alleles, I'm going to take 670 and multiply that times 80%, which is 536. How many carriers for football-shaped mouth are there? Okay, so carriers is a technical word here, meaning the heterozygous condition. We know that the percentage of the heterozygous condition is equal to 2PQ, and so we can do some math here. 0.2 times 0.8 times 2 is 0.32. And I know that there are 335 total individuals. So if I take that 0.32 then and multiply it times 335, I get the number of heterozygous individuals to be 107. And then what percentage of Bobs are homozygous dominant for the condition? So remember, homozygous dominant is the percentage of homozygous dominant is equal to p squared. And so then we're just going to take p and we're going to square it. And that's going to give us 0.64 or 64%. Moving right along. There's a small percentage of students at MHS who do not decorate for homecoming or who do not like to decorate for homecoming. These types are called fuddy-duddies, of which the biology teacher readily relates. Their trait for fuddy-duddiness is recessive in the population, and 40 of MHS's 450 students have it. Carriers of fuddy-duddyism are immune to rampant cynicism later in life, which is often the fate of many who demonstrate fuddy-duddiness in high school. With this information, answer the following questions. So again, before we answer any of the following questions, we're going to go ahead and do our thing. We're going to solve for q squared because q squared is the window to success in these types of problems. And I know that 40 of these individuals are recessive, meaning that they have both recessive alleles, and I know that the percentage of recessive percentage of individuals that have the recessive trait in a population is equal to q squared. And so in this case, q squared is equal to 40 divided by 450. And let's see what that number is going to be. That's something like that. And so then if I take the square root of that, I come up with 0.298, or let's go ahead and round it to a nice, comfortable 0.3, which means that p, because p plus q equals 1, that means p equals 0.7. So I know these things, and I'm going to go ahead and write these things at the top of my paper. And now I can answer that question. What percentage of the population is immune to rampant cynicism? Let's see. Well, the percentage of the population that is immune to rampant cynicism are carriers, right? Because carriers are immune, and so those carriers are heterozygous. And so that I know that the percentage of heterozygous individuals in a population is equal to 2pq. And so then I just do the math, and we're not going to get the calculator out for this one. That 2pq is 42%. What percentage of the population is homozygous dominant? And again, homozygous dominant is going to be p squared. And so then p squared is going to be 0.49, or let's be consistent, 49%. What is the percentage of recessive alleles in the population? Percentage of recessive alleles is equal to q. Therefore, that is going to be 30%. Now, here's a more open-ended question that doesn't involve math. If fuddy-duddyism isn't selected for in a population, why is it still around? So what do we mean by the language isn't selected for? First of all, the language isn't selected for is referring to natural selection. And typically when this language is employed, it is talking about the idea that nature isn't selecting for a trait, meaning that trait usually is unsuccessful. And so if a trait is unsuccessful, then why do you ever see that allele again? And it has to do with that recessive condition. Someone with the recessive condition or a carrier of the recessive condition is still viable. Natural selection selects for them because they show the dominant trait. And so then that recessive allele is hidden away, so to speak, until they mate with another individual with that recessive allele. And then that gives a chance for those recessive individuals to come back up. And so that's why the percent of recessive individuals with a bad trait, so to speak, will be few in a population. If you wanted to look at it in this population, for instance, notice that the vast majority of the population is fine, the 91%, but Q squared, or the percentage of homozygous recessive individuals, is going to be 0.09 or 9%. And so that's going to stick around. And so that is something to think about. And another thing that we could mention with this problem as well, carriers of this are immune to this. Why is that? It probably has to do with that idea that we talked about, the heterozygous advantage. So that's another thing that you could be looking for on a problem like this.